topic is about audit quality. So this paper, together with Professor Cho and Professor Miklos, about predicting audit quality using machine learning seems to be appropriate. So first about the background. So from the papers that you read for this class, we know that audit quality has been a focus of accounting and auditing research, especially after the SOX Act in 2002. And also the regulators today are still trying to improve audit quality. And the research papers that you read have identified some variables that are associated with audit quality. So we have seen Big Four or non-Big Four, right, the auditor size, and also the industry specialization of the audit firms. And some people also say, okay, the audit fee also has something to say with audit quality. So we have many papers that identify some variables associated with audit quality. So that's the first part of the story. And then, like in today's data environment, we can also have access to other variables that are related to audit from different sources. For example, we have audit analytics, the SIG Edgar, and a database called Bordex. So there are many variables or data out there, but these data have not been explored in the existing research. So we want to ask these two questions. First of all, among all the variables that have been studied in the literature and the variables that have not been explored, which of the variables are more related to or associated with audit quality? So that's the first question. The second question is, can we use these variables to effectively predict audit quality? So that's the two questions we want to ask. So why is it important to answer or to know these questions? So first of all, if the regulators know which variables are more likely to be associated with audit quality, they can use these variables as quality indicators to assess the audit quality of the engagement. And also, if they can predict audit quality, this model can help them target the audit engagements that needs to be inspected. For the accounting firms themselves, if they can predict the audit quality or the consequences related to poor audit quality, then they can remedy the unqualified practices timely. And for investors, they can also gauge the trustworthiness of the financial report they are reading. And for researchers, if we can identify the variables that can best predict audit quality, that can also help us in our audit quality research. So that's why it's important to answer these questions. And to address these two questions, this paper adopts an inductive research approach, which is very different from the traditional research approach, which is used in the papers that you guys read in this class. So the previous research relates to the audit quality, basically adopts a deductive research approach, where they start with a theory, and then they come up with hypotheses, and then they collect data, and then they use the results to confirm their hypothesis. For example, in the paper, do Big Four actually deliver higher audit quality, right? The first paper that you read, they first came up with a theory that, okay, Big Four firms have these such and such characteristics, therefore we would expect Big Four firms can deliver high audit quality. So that's their theory. And then their hypothesis is Big Four firms have higher audit quality, and they use the proxies to measure audit quality, right? So that's the hypothesis. And then they go to collect data from different sources, and then they perform the regression or different statistical tests to confirm. So this is called deductive reasoning. However, this paper is not trying to test any theories or any hypotheses. We just want to identify what are the variables that are most associated with audit quality. So we start with all the data that is available, and then use statistics to find the patterns, and then get the results, which can be potentially useful for future research that wants to do deductive reasoning. So this method is called inductive reasoning, or some people call it exploratory research. So this is the difference in terms of methodology compared to the papers that you read in this class. So specifically, this paper explored about 50 publicly available variables related to audit, and we explored 6 common machine learning algorithms. And later I will explain these in detail. So this is a summary of the results. So among the 48 audit-related variables, these 14 variables have been identified as the most predictive. So tenure means the length of auditor-client relationship. For example, I have audited Miklos for 5 years, so 5 years is the tenure. And then the second going concern opinion means whether the auditor issued going concern for that client. Fee ratio is the non-audit fee versus audit fee, so that's the ratio. Busy season means whether the audit engagement is in March. Same state means whether the client and the auditor are in the same state. And the number 6 means whether they have issued 10K late. So this is called non-timely issuance. And then the integrated audit is whether this engagement is integrated audit, meaning whether they also have internal control over financial report included in the audit. And auditor size, that's very intuitive. And the market share, portfolio share, auditor change, whether there is a change of the auditor. And then these are the specific reasons for the auditor changes. So you notice that some of the,
yes. A couple of comments. What Abby is doing here is what I always suggest all of you to do, is you start your paper presentation with what you're doing and tell the results as soon as you can. Because you go and present at Rutgers, Professor Alice starts asking questions in the first hour and the first minute, and you never get to the end of your paper. And when you see experienced guys presenting, they can keep my call, let me finish the paper, I'll come back and accept it. But for you guys that are novices, better that you put your results out as fast as you can, and then you come back and explain what you did. That's very, very important for the long range. Now, that was my first question. My second question was from Abby. Abby, can you explain me a little bit better what the integrated audit is?
Oh, so that's like whether so before that, the internal control over financial report was not included in audit engagement. So if the audit engagement has both the financial reporting and internal control over financial reporting, that's an integrated audit.
And how did you measure that?
So there is that variable is available from Audit Analytics.
Okay, so that's their definition, because I never really heard that terminology.
Yeah, that's their definition. So I will go to that part, the data collection part. So you notice that some of the variables are in bold and some are not. So the variables in bold indicate are the variables that have not been explored in the existing literature. And those that are in normal font means that they have been studied before. So this also indicates that from this study, we actually identified new knowledge for future research. And then in terms of the effectiveness of prediction, we identified some classifiers, the machine learning model that are very effective. And these are the random forest and artificial neural net.
Sorry, did not understand, but what is the dependent variable here?
Yeah, we'll get to that part.
Okay.
Yeah. So this is to address Jumi's question. So what is the dependent variable? Meaning, how do we measure audit quality? So in the paper, do practitioners measure in accordance with the PCAOB's measure of audit quality by ODIA? So in that paper, he compares different proxies of audit quality with the PCAOB standards. And he finds that, okay, among all these publicly available proxies, restatement is actually one of the best indicator of audit quality. And also based on other literature, we decided to use restatement that are material, meaning the restatement has to be disclosed on the 402 item in the 8K reports. Because these, if you disclose anything on 8K form, it means that it's very serious, it's material. And some people also call this type of restatement big R. So first of all, we say that, okay, this type of restatement has to be material. And second of all, the financial reports that have been restated have to be annual reports because the auditors only need to audit the annual report. So if the annual report has been restated, then it indicates more serious problem. So in this research, we exclude quarterly restatement. And then for the reasons of restatement, we focus on the gap violations because the auditors are responsible to identify the issues that violates the gap. So these criteria are all selected from the existing literature. And you can find a lot of research that use this proxy for quality. Yes?
Sorry, the reading that we need to read, the title of it is a review of archive or something, the really long paper. So that mentioned that the audit quality, definition of audit quality is like not whether it's acceptable or not.
That's
Or
right.
like the quality of it. Or don't you think that restatement is actually just covering whether it's acceptable, so binary value, so instead of like.
So this is an issue that has not been addressed in the academia because as a researcher, we can only rely on the data that is available. So, so Defunct and Zhang, they have a very, I actually cited their paper here. They actually have a very decent definition for audit quality. However, we cannot find data to realize that. So currently, still many researchers use this restatement closely for audit quality. But I highly encourage all of you to find more like measures because if you can solve that problem, that's going to be very, very, that's going to be a huge contribution. So as I said, the restatement is an okay proxy for audit quality, but it has its own limitations, right? As Julie said, you still cannot capture other aspects of audit quality. So that is the limitation of this research and many other audit quality research. So this is a common issue shared in this community. So we know this issue, however, this is what we can get best. So that's how we measure the audit quality. And then about the independent variables. So the independent variables contain two parts. The first part contains all the variables that have been studied before that are identified to be associated with audit quality. For example, the ones in bold in this list, whether this auditor is new, right, auditor change, whether it's Big Four, the tenure, whether there's a going concern opinion. So we went through the literature and find the variables that are associated with audit quality. And then we get another part just from audit analytics. These are the variables that are available but have not been explored in the literature. So we include these two parts. And so the reason we, so basically this research just used the publicly available data here, right? So because you may argue, okay, the hours or the effort the auditor spend in each engagement also relates to audit quality, right? However, that data is not available, right? It's private. So this research can only utilize the publicly available data out there. So this is another limitation of this research. And after we get the dependent variable and independent variables, we try to use the machine learning to find the patterns inside the data. So for those of you who don't know about machine learning, here's a brief introduction, and later I will compare machine learning with econometrics method that we use. So first of all, we all hear about AI, right? Artificial intelligence. So actually, machine learning is one subset of AI. So that is one of the methodologies to achieve intelligence. And in its core, machine learning is actually a computational method that can help us identify the hidden patterns inside the data so that we can identify associations and patterns. Okay, here's a table that I made to summarize econometrics and machine learning. So in econometrics, I believe most of us have taken courses in econometrics, and I myself was rigorously trained from this branch actually. So first of all, in terms of the main purpose, in econometrics, we want to test hypotheses. We want to identify causation, right? Whether this phenomenon caused some consequences, or they want to identify some associations. So that's the purpose of econometrics, and it is a very common method in accounting, economics, and finance research. However, for machine learning, the purpose, the goal is just to identify patterns. So the causational relationship is not a big issue in machine learning. We just want to identify patterns and associations. So that's the difference in the purpose. Second of all, in terms of assumptions that we need to rely on. In econometrics, I believe people who have learned about it knows that if you want to apply econometrics method, your data has to be very strict. Like you have to make sure that your data conforms with all those assumptions, especially like no zero condition or zero conditional mean, blah, 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 right? But when you use machine learning, you don't have to rely on these assumptions, and you just need to make sure that, okay, your data is reasonably a random sample. So that's the second difference. And then the third difference, in terms of models, in econometrics, we use regression, right? All kinds of regression, no matter it's OLS, logistic, or sometimes you perform time series. So in the machine learning, these models are actually part of machine learning that is called supervised learning. But machine learning contains much more, including unsupervised and semi-supervised. So that's the third difference.
Abby,
Yeah.
Can you talk about random sampling? Because very often in machine learning, we use the full population. So why you say random
okay, so random sampling just means that you can reasonably argue that your observations are not highly correlated. It's like in terms of height, in the whole population, the height is like a bell shape. So if your sample is similar to this, you can say that it's a random sample. So it's a little bit different from the sampling in audit that we mentioned.
Yeah,
So the random sample assumption just says that you need to make sure your sample or your data set is reasonably representative of the whole population. So that's
it's the whole population that you can measure.
Yeah, but there are still some differences because let's say when you get the data from CompuStat or the analytics, sometimes you need to delete the observations with missing value, right? So it's still not full population. It's still a sample of the population. So there are other differences, but I will not get to that part because the first three are kind of the main story here. So if the main purpose is that we want to make prediction rather than testing hypotheses or validating theories, we can use machine learning method rather than using econometrics. So that's why we choose machine learning in this research setting. And we basically compared 6 machine learning algorithms, and I will not go to the details, but these are more like technical part. So this is how we get our sample.
They call these the horse races. You learn several algorithms of machine learning, and you choose the one that gives you the best results. And the word that they use is horse races. I don't know why, but
Yeah, but basically, people want to compare the common algorithm and see what is the best performance. Because you cannot say that, okay, I directly use random forest. And then people will ask, how can you start with random forest without knowing the performances of other algorithms? So people usually start with comparing different algorithms and choose the one that has the best performance. So our data just come from the audit analytics because it is a relatively comprehensive data set related to audit. And we get the dependent and independent variables, and then we ended up with more than 100,000 firm year observations from 2000 to 2018. So this is to address Professor Miklos' question whether it's a full population. So the full population, you can say that it's actually about 300,000 observations, but we need to delete some observations from outside the US, some with missing data, so we ended up with 1/3 of the full population. So it's still a sample. However,
yeah, I actually wouldn't call that a sample. You're selecting your population to the correct population. The sample is typically people think about random samples, which is a subpopulation. Here you are kind of limiting the population to the relevant population.
That's okay. Okay, so the reason we started from 2000 is because the audit fee data is available from that time, and we ended at 2018 because there is a research showing that there is usually a 2-year lag between your financial statement and restatement. So people use 2 years to identify the issues. So now it's 2020, so that's why we moved 2 years forward. In total, we have 3.65% of the population that has material annual restatement. So later I will address this issue because if you have a very imbalanced data like here, you need to do some adjustment to your method to make sure that you consider this imbalance in the data.
Can you explain to them what you mean imbalance data?
Okay, so a balanced data is like female or male, right? It's usually like 50% male, 50% female. This is a balanced data set. But when you have an unbalanced data set, you will have a very skewed distribution like what I have here. So only 3.6 or less than 4% of the population got restatement and others are okay. So this is highly biased. And this can cause trouble because, can I have markers here? Okay. So let's say you have an algorithm that can give you prediction, okay? So now your data set has 96 negative observations and you have 4 positive observations. So let's say you have a very naive algorithm, and whenever you ask this algorithm, okay, is this observation positive or negative? And then this algorithm can every time give you, oh, this observation is negative. So when you give 100 observations to this algorithm, it will give 100 negative predictions. So what's the accuracy? It's 96%. However, is this algorithm informative? No, because whenever you ask him to predict, this algorithm will just give you a naive prediction that this is a negative instead. It has no information, right? So when your data set is highly unbalanced, this is the problem you will get, which means your algorithm can learn nothing, but still can give you a high accuracy. So this is the issue that we need to address when you have a imbalanced data set. Our sample or our data is representative of the full population, because if we look at the summary statistics, first of all, okay, I saw some people put the question in the discussion board that the PCLB inspected 50% or more of the Big Four firms. Is this really representative? This is the case because Big Four firms have more than half of the market share in the United States. So it's not because PCLB just want to investigate more Big Four firms. It's just that Big Four firms are too big. They just take more than half of the market share. And this is also true from our data set. 57% of our of the firm were audited by Big Four firms. And this leads to another issue of whether the Big Fours should be broken up. So I think that's another issue that people can think about. But anyway.
Abigail, when you quote the statistics, are you quoting for the publicly traded company?
Yeah, just public firms, yes. So in terms of the research design, I will just skip that because that's just not very relevant to this class. But I want to say that, so we did a horse race of different algorithms, right? So logistic regression, the second column, and random forest, knife base. And then we asked each algorithm to select the best set of features. So if there is a 1, it means that that algorithm selected this particular variable. And then we mark the variables that have been selected by most of the algorithms. That's how we identify the variables that are most predictive. That's where the least.
Is there any reason that you leave the decision tree empty?
Yeah, decision tree is DT.
So is there any reason that you didn't fill up that decision?
You mean here?
Yeah.
So if there's no 1, it means that the algorithm didn't select that variable as the predictive one. So I know that the AI students are now taking the machine learning, so you will get to that part about feature selection. So 1 just means that algorithm thinks that this variable is predictive, and 0 means no. So the variables highlighted in yellow are the ones that most of the algorithms think that variable is predictive. So these are the ones we selected as the most predictive. Okay, so here's the part where the machine learning can be combined or can be integrated with econometrics or inductive plus deductive. So in this step, we identify the variables that are predicted, right? However, we don't know in which direction can these variables predict. Meaning, okay, now you identify whether there's an issue with the audit opinion, can be associated with audit quality, but in which direction? Meaning, if there's an issue, does it mean that it indicates higher or lower audit quality, right? So that's what we don't know. Therefore, we run this econometrics regression to identify the direction. And so from the step, we compared the direction from our results with the previous literature, and we found that the directions are consistent with the previous literature, which actually confirms their research results. And second of all, the variables in bold are the new variables, or the variables that have not been studied before. So these associations we identified can be used in the future research that wants to study or explain why, for example, why if the auditor and the client are in the same state, they have higher audit quality, meaning they are less likely to be restated. So that actually lays the foundation for future research. This is the insight we can draw from this part. And then this is the effectiveness of the prediction, and this is also a little bit technical. But the main takeaway here is actually the previous few slides that I showed.
Can we go back to those effectiveness for prediction slides and talk about them a little bit?
Okay.
Yeah.
So this diagram basically shows the performance of different algorithms under different conditions. So the higher the average AUC, the better the performance. So just by looking at this diagram, you will notice that the random forest, which is in this light blue, has the best performance, right? In most cases, especially after the misclassification cost reaches certain threshold. And then logistic regression, which is in green, has lower performance, but it's kind of stable. And same is true for artificial neural network. So the AUC is actually an indicator that people in machine learning usually use to evaluate the performance, which is similar to the R square that we use in econometrics.
Maybe one more thing.
Yeah.
Can you just talk a bit about the misclassification
Okay, so
cost?
I thought that's a little bit technical, but okay. So the misclassification cost is actually related to the imbalance of your data set. So let's say in terrorism prediction, okay, most of our people are fine, are good ones, right? But only one, let's say me, Abby, is a potential terrorist, okay? So if there is there is someone who can predict the future, who sits there and just look at everyone and say, okay, is Miklos a terrorist or not? Is Erdong a terrorist or not? Okay, so this person makes prediction. Is it, okay, in which case is more serious? Just tell me, okay, option one, Miklos is a normal person, but this algorithm says Miklos is a terrorist. This is situation one. Situation two, I am actually a terrorist, but this person says I'm not, and let me go. Which one is more serious? Second one, right? So in the second one, we say that this is more costly because I'm actually a positive instance, right? I'm a terrorist. If you let me go by saying that I'm actually not a terrorist, I will go and cause harm to the society. That's costly. For Miklos, he's a good person, but people suspect that he is a terrorist. So they lock him up and do some investigation. So there is tiny cost, but is that a huge cost? No, because he's not going to do harm to the society, while I am going to do harm to the society, right? So in this case, so this is about the confusion matrix that I didn't mention. So if you look at this diagram, the actual positive, so in the story that I just gave is actual terrorist. Actual negative is actual good person, okay? And the predictive positive means that you predict this person is terrorist. And predictive negative means you predict that this person is fine. So we call that, so if you look at the values there, if you correctly predict a terrorist as a terrorist, that is called a true positive, right? So if some people say, oh, and you are a terrorist, and I actually predict that you are a terrorist, then that's a true positive. However, if I am a terrorist, and some people say, oh, I don't think you are, that's called a false negative, because your negative prediction is actually wrong, right? So that's called false negative. And using the same logic, you can understand what is a true negative and what is a false positive. So in this case, the mistake of false negative is much, much costly than the false positive, right? So this cost ratio between false negative and false positive is called misclassification cost. So this is important because, as I said, if you wrongly make the prediction, you are going to face huge consequences. That's why in the machine learning, we can mimic the learning process that if you make a false negative mistake, you are going to be punished much more or more severe than the other mistake. So that is the use of misclassification cost. And that is a parameter that we can manipulate in our research setting. So that's why you see different levels of misclassification cost. So that's the interpretation. One thing I want to mention is about the research, the inductive versus deductive. So for a long time, the academia prefers the first approach, which is deductive, where you start with a theory and hypothesis and you collect data and then confirm or reject your hypothesis. And also people say that only in that way we are doing research. However, we are living in a big data domain and people are calling for relevance of research. So now the inductive reasoning approach is getting more attention these days. And in a conference that I've been to, people call for a balance between deductive and inductive research. However, this is still a long way to go because the traditional research mindset is still preferring the deductive reasoning. So I'm not saying anything about, okay, whether we should do this or that. It's just that we need to be open-minded to embrace different kinds of research. So that's